So what we are, so is it true or not? And the answer is it is true that the characters do form an orthonormal basis for L2 of the circle group. But how to answer that? So there we were trying, the first approach was to take the natural approximation based on, let's say, the first finitely many characters. First means these are indexed by integers, so let's take minus n to n. The projection of the function f to the span of these characters indexed by minus n to n is given by this gn. Okay, so that's the projection of f. And then what we are trying to show is that we have to show that gn converges to f in L2. That's the exact same as this statement that to show that there exist some finite superpositions is same as showing this as long as we stick to L2. But we don't know how to show this. Okay, we don't know how to show that these things converge in L2. So what often we do in analysis is to not directly work with spaces like L2, but with sufficiently nice functions. So here, for example, if we can show that for continuous functions, this Gn converges to F uniformly, okay, then it will also converge in L2. So you will have proved the theorem for continuous functions, but continuous functions are dense in L2 of t, so it will also prove it for all of L2 of t. So that's the idea. Question is whether such a thing is true, but that is actually not true. Okay, so that is not true. And what Fejer did was to do a further averaging. So when f is a continuous function, you define this. Okay, you can even define for L2 functions, but here we are taking continuous functions. Gn is this, the projection in L2, and Hn is it is called the Cesaro average. Okay, so this, so now let me give them the usual names. So they are usually not denoted by Gn and Hn. They are usually denoted SNF, and so this is an, and this is denoted sigma NF. So given NF, it's a linear operator which associates to it another function which is of this form. So here I just locally will use the notation Gn Hn, but this is fairly standard, SNF and sigma NF. So this is the Cesaro average. There is some accent somewhere, but I don't remember. Cesaro average. So what Fejer showed was that if you take this, SNF may be wide, but Hn will actually converge to F uniformly. And that is just as good because Gn is in the span of the characters, Hn is also in the span of the characters, being a finite linear combination of GIs. So these are linear combinations of characters converging to F uniformly, showing that the span of the characters is dense in C of t in the space of continuous function with sup norm, which means that they are also dense in L2 of t in the L2 norm. Okay, so that's I even got the proof of that. Okay, so now let us go back to this Gn and Hn. We want to understand Gn and Hn. And what I had reduced was Gn, I had written as f inner product chi k, and after some manipulation, we saw that it is actually f convolved with d. Okay, so I have not introduced convolution, but maybe it is a good time to even introduce that notation. So for f and g functions from the circle group to complex numbers measurable, we define the convolution. Okay, this f and g have nothing to do with that g there. We define the convolution. Just any two functions, we define the convolution denoted f star g of e to the it is f of e to the is g of e to the it minus s ds over 2 pi over the circle group. As you know, many times I just write t, not so we also write We also write like that. I mean, that is fairly common abuse of notation. But of course, this doesn't always make sense whenever the integral exists. Whenever that integral is finite. If this is finite, typically so usually the way it should not depend on t. I mean, we would like to define f star g as a function, not for a particular t. So we will be interested in conditions where this will happen for all t. Okay, so almost all t. And there are many conditions. For example, if f and g are both integrable functions, then this is true for almost every t. So there is no problem, and it will define. So anyway, for now, it's just a notation. It's a very important operation. But we have seen the discrete convolution. In discrete groups, it was like f of x, g of f of y, g of x minus y summed over y. So that kind of stuff. So the only reason I'm introducing this is that this what we got here is actually a convolution. This is f star dn of theta. Okay, so that's what is the convolution. Where dn, this is called a Dirichlet kernel. Is basically summation chi k of theta chi k of phi bar k equals minus n to n, but that is e to the I k theta minus phi. It depends only on theta minus phi. So we make it a function of one variable. dn alpha is e to the I k alpha, where k is summed from minus n to n, and we, by pulling out the first term and summing the geometric series, we saw it was given by sine of n plus half alpha over sine half alpha. It kind of looks like this. The relevant portion is only minus pi to pi. Since it is the new denominator is positive, sine alpha by 2, alpha by 2 is going to be between minus pi by 2 to pi by 2. So that's a well-defined thing. I mean, it is always positive, non-negative, I mean. So this one, since it oscillates n times, it is going down. But since this is increasing with alpha, this dampens the thing. So these peaks are becoming smaller and smaller. And at alpha equal to 0, there is no problem. This has a limit. If you let alpha go to 0, what is this value? You know, sin x behaves like x as x goes to 0. So this will be like n plus half divided by half. So this value is n plus half divided by half, which is 2n plus 1. So that is the peak value. And then it has these smaller bumps. And there will be n or so zeros, I think, n or 2n zeros. Times it changes sign. So that is the Dirichlet kernel. And okay, but anyway, our theorem is not about Gn, it is about Hn. We have to further average the G's. So let's come to that. So what is Hn? Any questions so far? Is it okay? So let's come to Hn, Hn or sigma n, which I also locally denote Hn of theta, is 1 over n, sorry, 1 over n plus 1 k equals 0 to n gk of theta, but gk is actually f star d, this, right? F star d sub k. F convolved with the Dirichlet kernel of the kth order, k equals 0 up to n. And that we will, so this is just nothing but we will write it as f star kn of, see, convolution, if you do f star g1 plus g2 is f star g1 plus f star g2. That's obvious from here, the integral formula. So this is same as f star kn of theta, where what is kn? Kn of theta is 1 over n plus 1, k equals 0 to n, t sub k of theta. Okay, it is the average of the Dirichlet kernels of the first n plus 1 Dirichlet kernels. Okay, That's what it is. What is it? We want to find an explicit formula like this. It will be instructive. We will do that. I mean, it will be useful also. So this is nothing but we are summing. Well, we know the formula for decay. It is sine k plus half alpha over sine k sine half alpha. So here it is. I have 1 over n plus 1 outside. And I also bring the sine alpha by 2, theta by 2 out here. And then I have the sum of sine of k plus half theta, right? Which I will write as sines. I mean, if you remember trigonometry well, you will remember the formula for adding sines. But I find it always easy to write in terms of complex exponentials. So if you take k equals 0 to n, so sine is just the imaginary part of it. So let's just write it as imaginary part of this one. Because this is a geometric series which I can explicitly sum. It is e to the, right? I mean, sine k plus half alpha is just the imaginary part of e to the I k plus half alpha, which is
theta.
Yeah, theta. So sine theta by 2. And then there is the imaginary part. And what do I have here? So let's pull out e to the I theta by 2 outside. And then it is e to the I k theta from 0 to n. So it is 1 minus e to the I n plus 1 theta over 1 minus e to the I theta. That's the geometric thing, right? Which, like before, we will try to write. This is actually real valued. I mean, so not fully. I mean, okay. So let me write it properly. So this one, maybe I reduce on the side and then plug in the next thing. So what is inside the brackets is e to the I theta by 2, and then I pull out e to the I n plus 1 by 2 theta. That will make it e to the minus I n plus 1 by 2 theta minus e to the I n plus, I pulled out n plus 1 by 2 theta here. So that's what remains in the numerator. And I also pull out e to the I theta by 2 here. That will make it e to the minus I theta by 2 minus e to the I theta by 2. Okay, and this cancels. Okay, something is. I don't. Yeah, actually, let me not even pull this out. This doesn't help actually. So let me leave this as it is. So there is no cancellation there. So I may as well leave it as it is. Let me leave it as 1 minus e to the I n plus 1 theta. So this cancels with this, and this thing is minus 2i sine theta by 2, right? E to the I theta by 2 minus this to minus 2i sine theta by 2, and then I have 1 minus e to the I n plus 1 theta. So what I want is, so what do I get here? So everything, so this comes out. So here I have 1 by n plus 1. This is a real valued thing, sine theta by 2. I can bring that out. So that gives me sine square theta by 2 outside. And I have imaginary part. So, okay, so let's write this as I times 1 minus e to the I into n plus 1 theta divided by 2 sine theta by 2. Right. So imaginary part of I times something is the same as real part of that. So it's just the real part of what remains is 1 minus. So I have a 2 also outside, right? Right. I have a 2 here. I pull out the 2 also. 1 minus e to the I into n plus 1 theta. Well, that is easy. So that is. So 1 minus e to the I n. So this whole real part actually is 1 minus cosine of n plus 1 theta. which is just to write it in a way, so 2 times sine square of n plus 1 by 2 theta. So 1 minus cos x is 2 sine square x by 2. So if we do that, the 2 cancels here and we arrive at this final formula, which is quite neat, which is 1 by n plus 1 remains. What I have in the numerator is a sine squared. And what I have in the denominator is sine square theta by 2. Okay, so this is the Kn. So this Kn, by the way, is called Fejer kernel. That was Dirichlet kernel. This is okay. So you may see here, this is sine of n plus half theta. Oh, where did it go? Sorry, sine of n plus half theta over sine of half theta. This is sine square, not n plus half, but n plus 1 by 2 theta over sine square theta by 2. So how does this look? This one, if you draw, it is again, how does this look? Again, it is peak that again, the denominator is going to be decreasing. So this is of, so it's kind of like this. It looks like this, except that it is always positive, right? I mean, non-negative. So it is, it may have zeros, but it is like this. So 0 and pi and minus pi. So it's always non-negative. And the value at the peak is what? It is n plus 1 by 2 by half squared. N plus 1 by 2 by half. I mean, this is like n plus 1 by 2 squared, theta squared. This is by theta by 2 squared. So you will get n plus 1 squared. That's the value at the peak, at the origin. Elsewhere it will be smaller, but it's always positive. That is the key point.
Sir, divided by n plus 1 will cancel one of them, right?
Ah, you're right. You're right. Sorry. Yeah, that will make it n plus 1. Thank you. So it's not, it is n plus 1 square for that, but this is, there is a 1 n plus 1. So this will be like this. Okay. So this is the Fejer kernel. It is actually much better than the Dirichlet kernel. We will see in what way. Okay. So the Fejer kernel's properties, the main property, once we write down the main properties, the rest will become easy to understand. Okay. So the main properties of first of all, it is for all theta in minus pi pi. This is clear because it's the square. Upward it was maybe not clear because di's do change sign, right? I mean dk's do change sign as I do in the picture here somewhere. This one does change sign because of this ratio of signs. But this kn is actually a sum of those kernels, but it is actually non-negative. Second, if you integrate over t, kn of theta d theta over 2 pi, then you get exactly 1. Now, if you are good at integration, you may try to integrate this, but there is no need. You can go back and integrate here. Okay, so the way to do this is, the easiest way to see it is actually not to do this integration. But see, kn of theta is the left side is 1 over n plus 1 dj of theta d theta over 2 pi, that integral j equals 0 to n. But dj itself, you remember, is a sum of the characters, right? I mean, so dj is, again, not to use the sign function, but just use the original definition. dj is the sum of chi k from minus j to j. So this is actually 1 over n plus 1 sum over j equals 0 to n, and this sum is actually sum over k equals minus j to j. What chi k, which is e to the I k theta d theta over 2 pi. Now it is obvious this is 0 unless k is 0, right? So this is the basic point which I have emphasized. 1 if k equal to 0, 0 if k not equal to 0, positive or negative, that is 0. So for each j there is only one thing that comes. So you just get in each j exactly one of these is 1 and the rest are 0. So you get n plus 1 times 1 and that cancels and you get 1. So I don't know if you can see it from here. I can't. I mean, for me, this integral is not so clear that I can do it. Ratios of two signs. Okay. So third property is the following. So these two are saying, if you like, it's a probability density actually. So these two are saying that it is a probability density. So third point is the following, that for any delta positive, if I integrate over the complement of that, so t minus, let me remove okay, let me write kn of theta d theta goes to 0 as n goes to infinity. This is the statement, okay? What is it saying? That its integral is always 1, okay? Firstly, there is no cancellation in the integration because it's non-negative. The integral is always 1, but if you take any small interval here, minus delta delta, then after a while there is nothing coming from here. The total integral from these parts is vanishingly small. That means it is constant. This is a probability density concentrating close to 0. So this is showing that probability density concentrates to 0. Around 0. This is the key property. So in probability sense, so this is, we would say, these are converging to the Dirac measure at 0. In analysis, such a thing is called approximate identity. Okay. So in some sense, it is converging to the Dirac delta function, so to speak. Anyway, we will see how these are useful. Okay. So now we can prove Fejer's theorem. Proof of. Any questions about this? Many of you may have seen the proof of Fejer's theorem anyway. It will be a repetition. In that case, it's okay. It's a very nice theorem. So how do we get, so these are the properties, and we know that sigma nf is f star kn. That's what I had shown. Sigma nf is f star kn. Kn is given by this, but the formula is no longer important. The properties are important. And what are we supposed to show? We are supposed to show that sigma nf, that is Hn, converges to f uniformly. Okay, so that's what we want to show. So let f be in C of t. Fix any epsilon positive. I want to show that sigma nf gets within epsilon of f. How do we do that? Okay, first pick a delta. So I'll pick a delta. What is the, okay, such that we will come to that. So basic point is we have to look at this difference, right? So we have to look at sigma n f of theta minus f of theta. We want to bound the difference uniformly over theta. But we have seen that this is f star kn of theta minus f of theta. But what is f of what is that? What does that mean? This is just f of theta minus phi kn of phi d phi over 2 pi minus f of theta which we can write as f of theta times integral kn of phi d phi over 2 pi. Because this integral is 1. We have seen that that's a probability density. That integral is 1. And this is f star kn. Okay, I had written, where is the convolution definition? One of the things about convolution is that f star g and g star f are the same. You can transfer, you can make a change of variable t minus s and bring it to the other side. Okay, f star g and g star s f are the same. Anyway, here it is f of theta minus phi kn of phi d phi. You can also write as f of phi kn of theta minus phi. This is more convenient here. So which is bounded by integral over t of f of theta minus phi minus f of theta. I put the absolute value inside. That's why the inequality. And then since kn is positive, I don't need to put an absolute value on that. I get this integral. So the point is sigma n of theta minus f of theta we can bound by the integral against kn of f of theta minus phi minus f of theta. The whole point is this: f is a continuous function. So when phi is small, then f theta minus phi and theta are close, so this difference is small. So for when phi is small, this contribution, the integrand will be small. On the other hand, when phi is large, we know that the integral of kn over anything more than away from minus delta delta will be small. So that's what we have to exploit. This helps in for small phi and this helps for large phi because kn is decaying rapidly. So which we'll write as, now we'll split the integral into minus delta to delta and minus delta delta complement in minus pi pi. That's what I mean. F of theta minus phi minus f of theta into kn of phi. Now what is this? So now I have to choose what is delta. I pick delta such that if such that f of s minus f of t is less than equal to epsilon if s minus t is less than equal to delta. Okay, if 2 points are delta close, then this is epsilon close. F is continuous function on a compact set. It's uniformly continuous. So what we get is that here this will be, since theta minus phi and theta are within delta of each other, so we get that this is smaller than epsilon. So we get this is smaller than epsilon times integral of kn. I can now even, so this is on minus delta delta, but you can even enlarge it to the whole set, which we will do in a moment. Here what do I do? This difference will just bound by 2 times the sup norm of f. That's what the difference. We can't say when phi is large, we don't know. They may or may not be close. So best we can do is 2 times the sup norm. And we are left with the integral of kn on minus delta delta complement. So we know that this goes to 0. So this is smaller than epsilon. So this quantity is smaller than epsilon because this is at most 1. The integral over the whole set is 1. This is at most epsilon. And this goes to 0 as n goes to infinity. Okay. So therefore, and these things, by the way, this bound, you see that the bound is independent of theta. The bound does not depend on theta at all. The theta went away when I bounded this by 2 times sup norm and this by epsilon. Therefore, what we see is that sigma n f minus f, if you look at the sup norm, the lim sup of that is less than equal to epsilon, which means that is 0. For any epsilon, this is true. So this is saying that sigma n f minus f sup norm is going to 0. That's the proof of Fejer's theorem. Okay. So that is the whole point, that you have this density which is kind of approximating the delta function. So we have to just make the argument like this. This is a very useful point. And yeah. Any questions, comments on this? By the way, how many of you had seen a proof of work? Oh, sorry. Is there a question first? Is there a question?
So this is only using the fact that it's a modifier, but are there other coordinates for which if you apply it to f, you get linear combinations of those basis functions?
Maybe you can make up, I mean, yeah, probably, I suspect. Maybe, for example, you could perhaps do another level of averaging. That should only make things better.
Right.
You can average the K1, you can average K0 up to Kn. That should only make things better for us. So that will be another kernel. Yeah. Linear combinations of characters. Yeah, I have not ever tried to see what that looks like actually. So it may be something someone is curious. What happens if you take, I mean, it will be just better. Qualitatively, it is not any different. But what is the kernel you get if you average once more KIs? So do you get something more? Yeah. So in principle, yeah. So there may be many others also. That's possible. So what Soumyendu referred to as modifier is this property that this is like, so there is the notion of approximate identity. So this, everyone may have seen the delta function. If you're an electrical engineer, you may even have used it rigorously or not. But so what these things are approximate. So there are different names. Modifier or approximate identity. So what it does is basically it is approximate identity. What does this mean? So these are approximations to the delta functions. To the Dirac delta function, which does not exist as a function. It is supposed to be a something which is such that delta of x dx is 1, but delta of x is 0 if x not equal to 0. So this is what Dirac delta function is. So such a function does not exist. But this is the approximation to that. So this has the property that they integrate to 1. And it is kind of vanishing away from 0. Okay, you can't have one function which does that, but you can have a sequence of functions which approximate this property. And wherever you have delta function use, you can replace it by these approximate identities and try to give a proper proof rather than a formal proof. That's the idea. So that is why it's called approximate identity. Identity means, the reason it's called identity is that if you think about the convolution, delta function is the identity for the convolution. So this also will have the property that f of x delta of x dx is f of 0. That's the property of the delta function. Okay. So you think of it as the probability measure with degenerate at 0. That's what it is supposed to be. But that doesn't have a density. So, but this delta, if it were to exist, would be a identity for the convolution. Convolution does this. If you look at this, if g is the delta function, then this is gives you f of e to the it, because only s equal to t contributes, you get f of e to the it. So that's an identity for convolution, and this is approximate identity. The word modifier, actually, that's not that's useful in a different context. It's the idea that you can start with a weird function, convolve with kn, and you get a smooth function because kn has smoothness. That's the more appropriate use of the word modifier. Anyway, so this is the idea. So these are approximating but it is not necessary. I have given exercises in the notes with more general properties where you can get slightly more general than this, 3 properties. which will under which you also argue the same thing, that f star kn will converge to f. Okay. Okay. So that's the. Any other questions? Okay. What is wrong with the dn? Okay. What was the problem with the dn? That is, why does f star dn, which is gn, not converge to f? Okay, why does that fail? Okay, so dn has this property. So first of all, dn changes sign. dn changes sign, but that's not so important, not the main point. It would be okay if it were to change sign, but what it is that it is unbounded in L1. Problem is, so in other words, so here what the exercise I have given in the notes is that you can drop this condition, okay, kn greater than equal to 0. But you put in a condition, okay, maybe I state here first. So d theta over 2 pi goes to infinity as n goes to infinity. This is the problem. So if this was not the case, that is, even if you drop the positivity condition here, but assume that integral of mod kn is bounded, then you can show exactly what I have shown. Okay, so that is the exercise in the notes. So the problem here is that this diverges. Okay, why does it diverge and why is that a problem? Okay, so that is what I would like to just quickly go over. So why? Why is that true? It is not too difficult to do that. I mean, so let's write. So dn of theta is sine n plus half theta over sine of half theta, right? Okay, and it looks like this. To remind ourselves, it looks like this. So where does it vanish? It vanishes at let us write some alpha k equal to when this numerator is pi, a multiple of pi, then that's when we have problem. So if it is pi times j over n plus half, j goes from, I think j can go from, this has to be within minus pi, so I get j can go up to n. Mod j is less than equal to n, so this is alpha j. So there are 2n plus 1 places where actually j not equal to 0. At j equal to 0, it doesn't vanish because there is also vanishing in the denominator and they cancel. So there are 2n roots of this function. Okay, so and on alpha j plus 1, it has a constant sign. dn has constant sign. So let's just look at the positive side. Okay, so I don't mean alpha, yeah, alpha j plus 1. I mean, yeah, so j greater than equal to 0, greater than equal to 1, and less than equal to n minus 1. So take any such interval where it has constant sign, some interval like this. So we have to calculate that integral, forget the sign, and then sum it up. That will give you the integral of the absolute value, right? So what is the integral on that? So if you look at the integral on alpha j to alpha j plus 1, first of all, on this, so I am taking alpha j here. Okay, so j is 1 less than equal to j less than equal to n minus 1. The other side you will get exactly the same stuff. So this is enough for me. So alpha j to alpha j plus 1. So this here, the sign, the denominator is an iterating one. So but that is decreasing. So sign is increasing. So as in the denominator, I can put sign of the smallest value, which is alpha j by 2. One over sine of alpha j by 2 and times integral on alpha j to alpha j plus 1 sine of n plus half theta d theta over 2 pi. See, this is a period of the sine, or period in the sense it is a kind of half period. Either it will be like this or it will be on the negative side. Okay. So let's put the absolute value here. Let's put the absolute, this is anyway positive. So let me put the absolute value on this. So the absolute value function will look like this, alpha j to alpha j plus 1. But the height it reaches is always 1. Okay. The sine function is not scaled down. It is always going up to 1 and coming down. So that means I can, it's exactly like the sine function. So if I take, it just rescale to this short interval. So if I take half of this interval, okay, middle half. On the middle half, what is the value here? Okay, what is the value? It is above, so it is like in the 0 to pi by 2. If you look at 0 to pi by 2, sine function goes like this and comes down. So what is the middle half here? Sorry, this is pi. This is 0 to pi. So this is pi by 4 and this is 3 pi by 4. So at this value, it is 1 by root 2, right? So I can write that this is greater than equal to 1 over sine of alpha j by 2. And on this, I'll just forget the rest of the integral. I'll only take in the middle part where the function is largest. So there I can bound it below by 1 by square root 2 times. What is the value there? The value is at least 1 by square root 2 and the length of the interval is alpha j plus 1 minus alpha j by 2 because that's half of the length of the whole interval. So this is what we get. Now what is this going to be like? I mean, so this one, anyway, sine is at least 1. Is less than equal to 1. So I can write this as alpha j plus 1 minus alpha j, you see, is actually pi over n plus half. That is this difference, and then there is maybe 1 by 2 or something like that. I just use this. Okay, so this is only going to help me. I could have just bounded by 1. So it's at most 1. So that's what I should have done. Yeah, I didn't have to write this. It's at most 1. I could have just removed and put 1 there. So you get that this is, okay, something is wrong here. This is true. Okay, sorry. This is true, but this is not good. Why? I'm going, when I add up, I'll get n times. There are n such intervals, right? When I add up, I just get a bounded number. It's not going to help. I have to use the sine alpha j by 2. Sorry. I have to use the sine alpha j by 2. So we will use that. Yeah, so it's not good to bound it like that. Alpha j is like sine. Yeah, so you understand, if I use this, this is correct, but it is not going to, when I add up, I get a bounded number. I want to get something going to infinity. So what I want to use is a better bound for sine alpha j. So we will use sine x less than equal to, sine x by x. I use the upper bound of 1, but let me use the upper bound of x. This is true. It is true for all x actually. So sine x is less than, so let's use here alpha j by 2, which is what is it? The two various things cancel. This is pi. So what I am left with is alpha j into n plus half, right? So that will give me pi j. Pi cancel. So basically I am left with 1 by j with maybe a constant like 1 by root 2 or something like that. So which doesn't matter. So now I get something better. Now when I add up, I don't get something bounded. Consequently, integral of mod dn of theta d theta over 2 pi is greater than equal to, I can 1 by j equals 1 up to n minus 1. I have a 1 by root 2. Actually, if I add up on the other side, I get 2. So anyway, this is greater than equal to something like log of n minus 1 or something like that. It's approximately like log n. Let me write like this. It's a constant log n, definitely. The constant is better than 1, but I don't care. So it is like log n. So this blows up. That's how this integral blows up. So what I have did was to show that the integral from here is like 1 over j. So you get the harmonic series lower bound. Okay, any questions about this?
Just so you had the greater than or equal to 1 by 2 root 2. The next step refers to the sigma of the things, right? Not just the. Is it a direct continuation?
Yeah, this is equal to, because I put alpha j is pi j over n plus half. So I put pi j over n plus half. N plus half cancels with n plus half here. Pi cancels with the pi here. 2 cancels with the 2 here. I'm left with a j and a square root of 2.
Okay.
And then I sum. Here I sum. This integral is the sum of all these integrals. I even left out the middle big integral like this, but that will give me a bounded number. It's not of any help. So I'm summing over these intervals and these intervals. So 2 times 1 by square root of 2 times summation 1 over j from 1 to n minus 1. That's like log n. Is okay?
Thanks.
Okay. So that is how this blows up. Now my point is, why is that a problem? That I leave as an exercise. Use this idea, construct a function in C of t such that f star dn of 0 blows up. Okay, use this, think about this. Construct a continuous function such that f star dn of 0. So C of t, by the way, C of t means if you write it out in minus pi, make sure that your function should be equal at these two endpoints. Otherwise, it's not continuous on the circle. Okay, so this goes to infinity. So hence, no way f star dn does not converge to f, even in pointwise sense, let alone uniformly. So this is how you show that. So try to make your construct your function to exploit this weakness of dn, namely this what we have shown. Okay? So I'll leave that. I think it is okay. Am I making a mistake here? No. Yeah, no, it should be okay. I think it is okay. Okay, I gave the exercise, but now I'm getting a slight doubt. Maybe it is not so easy, this one. Okay, actually, let me think about it. Maybe it is not that obvious. Your f should not change with n, of course. Right. So if you can make f depend on n. Okay, what is easy? Okay, now I got it out actually. Sorry. Sorry. I mean, I put a question mark here. I will think about it and either keep it or remove it in the notes. See, it is easy to do the following. Easier is to find Fn such that Fn star Dn of 0 goes to infinity. But of course, that is easy if you allow Fn to become large. But Fn stays bounded. Its sup norm will be always at most 1, but its convolution with Dn blows up. This would be easier because you don't have to construct one single function, you construct a sequence. From here to here, it is possible in the sense that this is what is the gist of, if you know Banach-Steinhaus. So this is the uniform boundedness principle in functional analysis. Should allow you to go from the here to there. I think now I'm actually confused. I'll have to think about this, but okay, this is the problem, but I will leave it at that. Any questions, comments?
Sir,
Yes.
Is there like a frequency domain interpretation kind of, like, for me Dn looks like the box in the frequency domain because this is the sinc function, and Kn actually looks like a triangle, which is like a convolution of two box functions in the frequency domain. So does that have got anything to do with?
Well, Kn, I don't know if that analogy is correct. Yeah, no, it is true that this is actually, I mean, so this functions, well, yeah, so Dn is exactly like, I mean, yeah, it's right. It is the projection kernel onto the first n frequencies, minus n to n. And
Yes.
it is just something that treats all these frequencies equally. It is an equal superposition, so to speak, of this first. You cannot take of all frequencies. That should give you the delta function, right? If you take all frequencies in your language with equal weight, you should get the delta function. But here you get, you cannot do that. You can take the first 10 frequencies with, that's what Dn looks like. Yeah, so this is, I mean, so the frequency interpretation is there. I don't know what further to say. I mean, I may not have any better idea. All I can say, another thing is that you may have seen this type of pictures. It's relevant. I mean, it's not coincidence that in optics, diffraction, and so on, you would have seen these kinds of pictures, that there is a central peak and then there are lesser peaks. So there are these images which there is a sharp image. Then there is a part where there is darkness, and then there is a sharp another peak, not as sharp as the previous one, and so on, multiple ones. So this is actually, I mean, so that is related, of course, to Fourier analysis. Yeah, but okay, I don't know a more precise answer to your question.
So I have a question, Manju. So
yeah.
So for this exercise kind of thing that you have written, suppose you take the signum function of dn.
Yes, but that depends on n. That's the
right. But then if you just you can't modify it
without depending on n. I don't know how exactly. Probably you can, but this would be the way you essentially suggested how to do this, so people can try this. So you can find something that depends on n, and then the uniform boundedness principle in principle gives you exactly that, how one function sort of comes. I mean, that's the idea, that you have a sequence of operators, and if they are blowing up, then they must blow. I mean, so if they are pointwise bounded, they are uniform.
Yeah.
That's the idea. So, but explicitly, perhaps one can work it out in this case. I suspect it is not too hard. I'm not sure though.
Okay, thanks.
Yeah. Any other questions, comments? Okay, so we have covered the main point of this. So let me conclude in 2 minutes I have. So what we have is, so let's define. So for f in L2 of the circle, I always mean with d theta over 2 pi measure. Okay, L2 of t, define its Fourier coefficients, its Fourier transform, f hat from z to complex numbers by f hat of n is f inner product En in L2 of t, which means just as usual, the inner product against a character is what we call the Fourier coefficient, right? And the characters here are indexed by integers. So f hat is a function on characters or function on integers, either way you want to phrase it. F of theta e to the minus I n theta d theta over 2 pi. But as En's form.
It's 1 o'clock.
I used to write chi-n, but it is En. Now I'm back to En. Okay, En is e to the in theta. So En is an orthonormal basis. We get the recovery. How do you recover a function from the orthonormal basis? You just take f inner product En times En summed over n in z. So this should be interpreted. The equality is in the sense that if you take n equal to minus say capital N to plus capital N, f e n e n, this will converge to f in L2 of t. That's the meaning. It's not pointwise. It's not, even if people write f of theta equal to this with theta here, it's not true pointwise. It is in L2 sense. This exactly means, so this is maybe even better to write L2 of t. It just means that the partial sums on the right side converge to f in L2 sense on the this. And this is, and we also know that in such an orthonormal expansion, L2 of t norm squared is given by the sum of squares of the, so this is actually f hat of n. So let's not write f hat of n. So f hat of n mod squared. Because it's an orthonormal basis, the norm squared is given by sum of squares of coefficients, which I can write as f hat L2 of z squared. So all the things are here actually, the main things that I proved in, so this is Fourier inversion. So this is the Fourier coefficient, Fourier transform, f to f hat. How to get f hat from f? That is Fourier inversion, and this is Plancherel. In fact, a little more generally, I can write that instead of one f, you can take two functions, f and g, inner product in L2 of t. That will turn out to be f hat of n, g hat of n conjugate, because that's how the basis works. And that is f hat inner product g hat in L2 of z, where z comes with counting measure. So these are Plancherel relations. So it is all there actually. So in the case of this, it's very simple and it is there, except there is a little bit of strangeness compared to the finite abelian case, that on the left side L2 norm is in t. It's an integral square. Here it is a sum. And same with this Plancherel type relation. One side it is sum, another side it is integral. So what I will do is probably I will tell you the general story of what happens in locally compact abelian groups. So there is a natural setting. So the thing is, unlike in the finite dimensional setting, the dual, so what we will talk about is the dual of a group, and t hat turns out to be z. So it's not, unlike in the finite abelian case, the dual of a group is not going to be itself. But double dual will still be itself. Z hat will be equal to t. So this I will come to later. So what I want to say is that when you go to Fourier transform, unlike in the finite abelian case, they are on different objects. Functions are on t, Fourier transforms are on z, and conversely. Okay, so since I am not taking class on Friday, I thought I will finish this up. Okay, so no class on Friday. I will also post it on the Teams. I'll stop here now.